Now we'll talk about f being differentiable. And first, we're going to talk about tangent planes. Um, so the first thing we can say that if we graph the equation f of x, y, z equals 0, then we can see it as a surface. It is some kind of surface. Okay, and we're going to let f have continuous first partial derivatives. Okay, also let P0 be the point, x0, y0, z0 on the surface where the first partials of the function are not all 0. And then the idea is, as we get closer and closer to the surface, we can approximate the surface by a tangent plane through that point, or the tangent plane through the point. So, let's just, here's a surface, and here's a point on the surface. Let's just say it's like that. Then the tangent, let me draw a tangent plane. So this tangent plane, TP, and this is the surface. The tangent plane at this point just barely touches the surface, and if you zoom in on it or get closer and closer to it, that little piece of that tangent plane is going to approximate the surface. It's going to be almost the same thing. Just like in a curve, we can approximate it with a line to that point on the curve, and really close to that point, the surface, the curve, and the tangent line are almost the same. So it's the same idea here, but here we're talking about surfaces and planes. Okay, so I'll draw another picture, but first we're going to let C1 be the trace, or a curve, which is a curve, described by the intersection of the surface and the plane y equal y0. And C2 is going to be the trace of the curve described by the intersection of the surface and x equal x0. So this plane is parallel to the xz plane, and this plane is parallel to the yz plane. Okay, let me draw a picture of that so far. These are kind of hard to draw. I'm going to use maple in a minute. Again, I do the same surface because it's just easier. There's my surface. And let's let this be x0, y0, and let that be p0. Okay, now the trace, the C1, is in this plane right here. Let me just draw a little bit. This is the y equal y0 plane. Remember, it goes off in all directions. So that, if I trace the curve, will look like that. That's going to be C1. The x equal x0 plane is this plane right here. Again, it goes in all directions, and that's if that intersects with this surface, then it's going to go look something like this. And we'll say that's C2. Now let me define a few more things. Let me take the red, or let's take dark blue. T1 is going to be the tangent line to C1 at the point P0, which is right here. And T2 is a tangent line to C2 at the point P0. So in green, we have this tangent line. That's T1. Again, that's tangent to the surface. And we have this tangent line, T2. Oh, sorry. And that forms this plane. Those two lines form a plane. So the definition of tangent plane, it's a plane that contains T1 and T2. And that's unique. Two lines determine a plane. All right. Now let's talk about equation of that plane. Plane equation through P0 is represented by A, x minus x0 plus B, y minus y0 plus C, z minus z0 equals 0. And we're going to divide everything by C. And we get z minus z0 equals minus A over C minus B over C. And we're going to let that be A, and we're going to let this be B. And then we're also going to let y equal y0, so we're in the plane. We're intersecting the tangent plane with the y equal y0 plane. Oh, let me write that down. We're intersect the tangent plane with the y equal y0 plane. And we get z minus z0 equals A times x minus x0. The y minus y0 drop out, goes to 0. So we get these two equations simultaneously. Notice this equation of a line. The A is the slope of the tangent line, which is also f, the first partial of f with respect to x at that point x0, y0. And then we can also let x equal x0, so we're intersecting the tangent plane with the plane x equal x0, and we get a line. When you intersect two planes, you get a line. So here we're going to get this. And this is the slope of the tangent line to, let's see, this is the first partial of f with respect to y, x0, y0. So substituting those back in, we get this equation, that's a star, z minus z0 equals f of x, x0, y0 at x minus x0 times, plus the first partial of f with respect to y at the point times y minus y0. Now, we're going to talk about a linear approximation, or you can also call it a tangent Let's see what the book calls it. They call it a tangent plane approximation. Remember, again, you're approximating the surface at a specific point with a small area of that plane that's tangent to it. Just like a linear approximation, you take a regular curve and you approximate it with a line. And let's say at the point AB, instead of x0, y0. So then we have z is going to equal first partial of x at AB times x minus a plus f of y at AB times y minus b plus z0, but z0 is the function evaluated at a, b. So we're going to take this and we call this the linearization of f at the point a, b, and we're going to call it L of x, y. Now you'll see how we do a problem in the example homework problems. I'm not going to do an example here because you can just look at those. But what we're going to say is that the surface at the point is approximately equal to the tangent plane equation at a point AB, and this is approximately equal when we're near to AB. Again, we take a surface and we're just approximating it by a little piece of that tangent plane. I know the tangent plane's flat, but if you zoom in far enough, then you can get the surface to be approximately flat. So we're going to say f of x, y is approximately L of x, y near the point AB. It has to be near a certain point. If you go too far, then the tangent plane's going off probably in a different direction than your surface. So you have to stay really close to your point. And again, you can see the homework for an example of this. Let's talk about f being differentiable. Just like if y is equal to f of x in 2 dimensions, then we define delta y to be f prime at a, where a is a certain point at x, delta x plus epsilon delta x, where epsilon goes to 0 as delta x goes to 0. So those things get very, very small. And then we're going to say that f is differentiable. Let's go to 3 dimensions now and see how it relates. At a point AB, if delta z, which we define to be the first partial with respect to x, at AB delta x, plus partial with respect to y at AB delta y, plus a small piece of delta x, and plus another small piece with delta y. And epsilon 1 and epsilon 2 go to 0 as delta x, delta y go to 0. Okay, but that's a really hard definition to prove. But I just wanted you to see how it looks compared to the 2-dimensional definition. It's pretty much the same. And we're going to use this theorem, which I'm not going to prove, that says if the first partials exist near our point and they're continuous at the point, then f is differentiable at the point. And you really should take a look at the proof of that theorem, again, that's in your text. Actually, it's in the appendix, but that's a proof that you should look at. So that's a way to show that your function is differentiable. Okay, then we'll talk about differentials. Let's look at the two-dimension case. In two dimensions, if y is f of x, then dy is defined to be f prime of x times dx. So if z is a function of x and y, then dz or df is defined to be the first partial with respect to x plus the first partial with respect to y dy. So first partial with respect to x dx plus first partial with respect to y dy. We could do it like this. We could say let a equal x minus delta x and b equal y minus delta y. So this is also equal to f of x at ab, x minus a, plus f of y at ab, y minus b. So let's see what this represents. dz is a change in height of the tangent plane as you move from x to x plus delta x. And delta z is a change in height of the surface from AB to A plus delta x, y plus delta y. Or B plus delta y. So we can approximate that change using dz, the differentials. Remember, if you're just in two-dimensional case, let's go back, dy is the change in the tangent line. So if you have this curve, tangent, let me make a better picture. Okay, the change from here to the actual curve is delta y. The change from there to the tangent line is dy, and dy is approximately delta y. And that's the same thing in three dimensions. If you think of this line as a plane, as this line right here is a plane, and this is the surface, it's the same idea. The change in height of the actual surface is delta z. The change to the tangent plane is dz, and they're approximately the same. So let me go back and find where I was. That's the approximate, and this is the actual change near the point AB. Okay, look at the sample homework problems to see some examples done for you.